Hey everyone, welcome back. This is SMC 2001, question number 23. So this is a question that someone requested me to go through, and I think it's really quite a difficult question actually. Okay, this is one of probably the most difficult questions that they could ask in terms of geometry. Okay, so yeah, I think really do try this out for yourself if you haven't already seen this question. It's very difficult. The reason why it's difficult is because we have effectively this sort of bit at the bottom of the circle here, right? So that just makes this problem sort of quite difficult, right? Because if we have this gap at the bottom of a circle, and we want to calculate effectively the side lengths of our equilateral triangle, okay? And if there was no gap, then it would be easier to calculate things like, for example, this height here, right? Because effectively, what we would know is that the radius of our circle, and we would be able to figure out this height here, so we would be able to easily figure out the bottom height if there wasn't this gap, right? And so if you can figure out the height of that equilateral triangle, then you've pretty much got the side lengths, right? So it's pretty easy. But sorry, I haven't even shown you the question as of right now. I'm just telling you that that's why this question is so difficult. Okay. But I'd say it's simpler than definitely SMC 2000 question 25. I think that question was harder than this, but it's question 23. The question 25 from this year is another geometry problem, which I'll go through in a different video, but it's a quite a good one as well. So anyway, an equilateral triangle is inscribed in the circle as shown. Another equilateral triangle is drawn in one of the segments so that the final diagram has a line of symmetry. What's the ratio of the length of the side of the bigger triangle to the length of the side of the smaller triangle? Okay, so ultimately we have this these two equilateral triangles. So obviously all the angles are 60. The sides are the same. Well, the sides of each individual equilateral triangle are the same, and effectively the way that we've sort of defined this configuration uniquely is by effectively saying that once I've placed down this larger equilateral triangle, I want to place down the other equilateral triangles such that I have this line of symmetry, right? So effectively I can cut it in sort of that vertical, cut it with this vertical line here, and then my left side and my right hand side of these are effectively just the same, okay? Of the resultant sort of shape, the resultant like stuff that I'm left with after I make that cut is the same on the left hand side and the right hand side, okay? That's basically the rule here. And so as a result, right, so effectively because of this line of symmetry, we can also make the conclusion that this length here is actually the same as this length here, okay, which will be useful later on. So really that's kind of, I guess, one of the main things that comes out of that line of symmetry, right? Because if there's a line of symmetry, then effectively it means that lengths, effectively when you reflect one side onto the other side, it will just stay the same, right? So it's like a line of reflection. And effectively when I reflect anything on the right hand side of that sort of like circle, it will just get the thing on the left hand side. And so distances are preserved on the reflection, and so you can get that concept that the distance will remain the same onto that reflection, right? So that's basically the main idea. Okay. But that's kind of just semantics though. Anyway, so that's really why the fact that it's symmetrical is good. And then what we actually define though is effectively the ratio of this larger side to this smaller side. Okay, that's basically what we're looking for. So we don't really have any numbers here, right? They haven't given us anything, so that might immediately alarm you. But if that's the case, then you need to think about why that's the case, right? In this specific example question, really the reason for that is because they're asking to find the ratio. Okay, so ratio is going to be obviously irrespective of how much I scale up my circle, right? So the scale of this circle is irrelevant. Okay, if my radius of the circle is 1, then obviously when I scale it up to 2, obviously the ratio should stay the same, right? Well, they're kind of implying it does stay the same, right? Because otherwise they would give us some lengths. So the fact that, so you can basically deduce things based off of what they haven't given us. So that's another trick that you should be using in the SMC, is trying to make deductions based on what they, give you first of all and don't give you. Okay, so both those things are important. So don't forget about that. Okay, right. So how exactly are we going to go about this though? So first of all, what we can do is we can obviously then we can introduce a specific example, right? Because we can just introduce a number, right? So for example, we can say the radius of our circle is 1 unit. It doesn't really matter what that unit is because it's a ratio, so it'll be dimensionless. Effectively, we won't have any units anyway. So 1 unit, right? And obviously this could be anything, right? It could be any unit I want. Okay, it doesn't matter because the ratio will always be the same. So yes, it could be 1 unit, 2 units, but just for sake of simplicity, we'll choose 1. Okay, because it's a nice number to deal with and it's reasonable. Okay, that's pretty much the only reason for the choice, right? So then effectively we label the center of the circle O here, such that obviously the distance from the center of the circle to sort of the vertices of the triangle, which obviously touch the circumference of the circle, will just be 1. Okay, and so when you do this, you're obviously going to get isosceles triangles, okay, and since they're all the same, effectively, because they each have two side lengths 1, then effectively this angle here is also going to be the same in all of them. Okay, and it's an equilateral triangle, so this length will be the same for all of them. So the triangles are exactly the same, and each of these angles is 120 degrees. So now it's very easy for us to figure out the side length of the equilateral triangle by just using the cosine rule. Okay, so using the cosine rule, what we get is that a squared is equal to b squared plus c squared minus 2 bc cosine 120. Okay, now remember for your rules, cosine rules, very important one, is that cosine of 90 plus x is minus sine x, okay? This is just an important rule to remember. So in this case, x is 30, so cosine of 120 is minus sine of 30. So a squared is effectively equal to 2 minus 2 times minus sine of 30. Okay, so this is just going to be equal to 2 plus 2 sine 30, so minus and a minus makes a plus, and sine 30 is just a half. Okay, this is a value that you should remember your sine values. So sine 30 is a half, sine 45 is root 2 over 2, sine 60 is root 3 over 2, sine 90 is 1. Okay, and obviously the opposite way around for the cosine. And your tan, obviously you can derive those, but probably also important to remember those as well. Okay, so this sine of 30 is a half. Although admittedly, I don't think you see tan as much. We see cosine and cosine, but I'm not sure. You do occasionally see tan, so it's important to know. So sine of 30 is a half, so you have 2 plus 2 times a half, so that's just 2 plus 1. Okay, which is 3. So a squared, so that's side length of the triangle squared, is 3, which implies that the side length is root 3. So obviously lengths are positive, so we take the positive root. So obviously then we have one of our side lengths that we want to calculate. So that's basically, we would assume part of the problem, but really the trickier part of the problem, right, is finding the length of the smaller equilateral triangle. So how are we going to do that? Okay, so we need to first of all calculate a few other things, right? So let's just get rid of what we have, everything else here that's irrelevant, right? So we have that root 3. So that you need to remember, obviously, for the ratio. We have the center of a circle here, right? And we have these sort of, I'm going to take this specific triangle here. So that's side length 1, that's side length 1. And obviously this is a side length of the equilateral triangle, so it's root 3. That's 120 degrees, okay? But let's just get rid of that for now. Okay, so obviously now, if I were to draw if I were to form a sort of vertical line from the center of the circle down, then effectively what I'm going to get is, because it's a vertical line, right, and this line here is effectively horizontal, what I'm going to get is just, these are both 90 degrees, right, and by the fact that there is sort of this symmetry to the shape, this length is going to be the same as this length, okay, and so effectively what you can immediately see is that these two triangles are going to be the same, okay, and since these two lengths are equal, and the entire length of the bottom side is root 3, so each of the lengths there will be just root 3 over 2, right, and so we can now calculate this length here, right, this height, just via Pythagoras. So via Pythagoras, so that's going to be x squared is equal to 1 minus the square root of 3 over 2 squared. So that's going to be equal to 1 minus 3/4, which is a quarter, right? Which implies obviously therefore that x is equal to a half, since obviously it's a length, so it's not going to be negative. So that length there is a half, right? So that height of that triangle there is just going to be 1/2. Okay, so that's the first piece of information we need to know. Okay, so now we can get rid of everything else. Okay, and then now that we know that, right, that's a half. We now need to think about how we're going to get effectively this length, or this length, right? Well, we also know, obviously, the radius of our circle is 1. Okay, so we know, for example, if I connect this to here, right, this is kind of just a construction that you kind of have to find. You need to experiment a little bit. Unfortunately, that's the way the SMC goes. You do have to do a little bit of experiment. They're not the easiest constructions to find. But this one is fairly not too bad, because it involves, obviously, a length that you can find pretty easily and our radius, right? So we're going to have a radius here of 1. So if I'm considering this triangle here, right, so this is length 1, because that's our radius, right? And so then this length we don't know. Okay, but we do know this angle in here. Okay, so if I actually just sort of draw this triangle out somewhere else, let me just try and draw it over here. I'm going to have something that looks a little bit like this, right? Okay, so that's of length 1, that's of length 1/2, and this angle here is what is the last piece of the puzzle, right? Because once we have that, we have enough information to find this side length, okay, which is the required length. So in order to do that, we need to now think, okay, so obviously we know, for example, that this this here is 90 degrees, okay? Because it's a vertical line, it's perpendicular to a horizontal line, okay? That should be fairly self-explanatory. Right, and then obviously we know that this angle here is 60, okay? The reason why that's 60 is because, effectively, it's an equilateral triangle. We're told that in the question, right? So we have 90 and 60, okay? And we also obviously know that this part of that angle is going to be 90. So the entire angle will be 90 plus the other angle. But now remember that because of the symmetry from the problem, this is another thing actually, because of the symmetry from the problem, effectively what we're going to have is that this angle is equal to this angle. Since again, angles are preserved under the reflection, right? So that angle will remain the same. And so effectively that means that we will have, right? So 2 times 90, which is 180, plus 60 from the equilateral triangle, plus 2x is equal to 360, and we can solve for x. And then we do 90 plus x to get our angle, okay? Because effectively, if you look at it, if I zoom out, then our angle is effectively some 90 plus another x here. That's what I'm saying, really. So obviously then we get, this is 240, then you do 360 minus 240 is 120, that gives you x is equal to 60 degrees, okay? So then this angle here is just 90 plus 60, which is 150 degrees, which should be telling you, which should be sort of screaming to you, okay, that has to be right, because sine of 150 is very simple to calculate, because as you should probably know, sine of x is equal to sine of 180 minus x, right, in degrees, where x is in degrees, okay? So this is just the rule, okay? And that means that it's very easy to calculate angles, sine of stuff with this, okay? Because obviously with triangles you need the sine rule, cosine rule, etc. If we have not nice angles, we're going to struggle to do that, okay? So SMC will always pretty much give you nice angles, so that you can do that without a calculator because you're not given one. So there you go, 150, that sounds right, and it is right, okay? So now that we have that angle, we can just basically calculate the side length of our smaller equilateral triangle. So let's just do that, but actually remember what you get it as, so let's just do it. So you're going to use the sine rule here. So we can use the sine rule to effectively say that 1 divided by sine of 150 is going to be equal to a half over sine x divided by sine x, okay? So effectively, That's going to be 1 over 2 sine x, effectively, so that's going to be 1 over 2 sine x. So sine 150 is the same as sine 30, so that's just a half. Okay, so 1 divided by a half is going to effectively just be 2. Okay, so 2 is equal to 1 over 2 sine x. So that's going to be 4 is equal to 1 over sine x. And effectively you're going to get sine x is equal to a quarter, which is a little bit strange, actually. A little bit strange. In fact, I don't think we need that piece of information, do we? Yeah, maybe we don't need that piece of information. I think maybe the thing that we're looking for is some sort of cosine rule, actually, now that I think about it, because otherwise you're going to get that sine x equal to a quarter, which is just a funky angle. I don't think that really matters what that angle is, but obviously you're not going to be able to undo this, right? You're not going to be able to do arc sine of a quarter, unless I'm mistaken, but I don't think you can do that without a calculator. Let me just check with a calculator to see if that's doable. I know it's cheating, but yeah, so it gives you about 14.477, so it's not an exact real angle, you're not going to get it, right? So that means that we have done something wrong, and I think the thing that we've done wrong is use the sine rule. I think we should instead use the cosine rule, so let's go ahead and do that. So the cosine rule effectively gives us that x squared is equal to 1 plus a quarter minus 2. A squared is equal to... Oh, no, sorry. I'm going to have to be careful about how I do this, right? How I label my A, B, and C. So let's label this A, this B, and this C, okay? Because then we have this angle. That's the only angle that we can ascertain at the moment, right? So obviously then we're going to have A squared is equal to B squared, which is a half squared, so a quarter, plus C squared, minus 2, B, C, cosine of 150. Okay, now cosine of 150 is minus sine of 60, right? Yeah, from our rule from earlier. So it's going to be 1 is equal to a quarter, add C squared, minus C, so plus C sine 60. So that's sine 60 is root 3 over 2, so plus root 3 over 2 times C. Now obviously, then what you can rearrange this, you get 0 is equal to C squared, plus root 3 over 2C, and then minus 3/4 effectively, right? So hopefully when I solve this, I'm going to get my side length, and then I can find my ratio. Hopefully, fingers crossed, this should work. Okay, so C is equal to minus B plus or minus the square root of B squared minus 4 times minus 3/4, so that's going to be plus 3, so that's going to be, and then all divided by 2. So that effectively gives you minus root 3 over 2 plus or minus the square root of 15 over 4, if I'm thinking correctly here. So it's going to be 3/4 plus 3, so that's going to be, yeah, 15 over 4 divided by 2. So that's going to be minus root 3 over 2 plus or minus root 15 over 2, and then divide it by 2. It's going to be minus root 3 over 4 plus or minus root 15 over 4. Effectively, that is the value that we're getting for our C. Okay, so that's kind of a bit weird, actually. I'm questioning whether I'm quite right here, but it could be right, actually. Because if you think about it, you're going to get what's that? So that's going to be root 15. Well, first of all, this is already negative, so I don't want to minus something from it. So obviously I'm going to have to take the positive solution here, otherwise I'm going to get negative length. So the real answer here that I want is this. And this is going to be equal to what? Minus root 3 over 4 plus root 3 over 4 times root 5. So we're going to get root 3 over 4 multiplied by root 5 minus 1. Okay, so this is our side length of the smaller triangle. So smaller triangle side length, smaller triangle side length. And now what we need to do is we need to find the ratio of the two, which is easy enough, right? So the ratio, obviously the other one is a root 3. So ratio is going to be root 3 divided by that. So ratio equals root 3 divided by, what's it? Root 3 over 4, root 5 minus 1. So what's it? Root 3 divided by root 3 over 4 times the square root of 5 minus 1. So what? That just inverts on itself. So it's going to be root 3 times 4 over the square root of 3 times the square root of 5 minus 1. So these cancel out, and you just get 4 divided by the square root of 5 minus 1. Okay, so that's the ratio, which I think I'm going to have to rationalize this. So I'm going to have to do times root 5 plus 1 divided by root 5 plus 1. That's going to give us 4 root 5 plus 4 divided by 5 minus 1, which is 4. Okay, because you get a squared minus b squared. Okay, so that just gives us 4 root 5 plus 4 divided by 4, which gives us root 5 plus 1. So the ratio of the two sides is root 5 plus 1. And if you look at your options, then you will see that that corresponds to option A. Okay, because that means that effectively we did the bigger divided by the smaller. So the bigger one is effectively root 5 plus 1 times the smaller one. Okay, and so there we go. That is the solution to this problem. Very interesting problem. Not too difficult if you see that, though. If you see that construction, the hardest part is this specific triangle here with the 1 1/2 150. That is by far the hardest part of this question. Once you've got that down, the rest is pretty straightforward. But seeing that takes a while. Okay, I think the first time I did this with some friends, it took us a very long time to find that. If we even did find it, I don't remember. But Yeah, it was a very, very difficult problem, and it took us a long time first try. Second try, I actually found this pretty quickly. So probably I remember in my head somewhere how to do this. But ultimately, yeah, very nice question. Quite an elegant solution. Awesome. There you go, for the guy that asked for this.